Thank you very much to the organizers for giving me the opportunity to present my work here. I'm going to talk about a completely different scenario of quantum gravity, but a friend of CDT, asymptotic safety, and scalar-tensor theories in this context. Work done in collaboration with Frank Saueressig, my PhD's advisor, Antonio Pereira, my second PhD advisor, and Yang Wang. So let me start with a brief motivation. So here's the Einstein-Hilbert action of general relativity, and we know the theory has some problems. For example, it shows at the classical level space-time singularities, while at the quantum level, we know that the theory is perturbatively non-normalizable. This tells us that GR can at most be regarded as an effective field theory, and we lose predictivity when we go beyond the regime of validity of this effective theory. By contrast, asymptotic safety is a candidate for quantum gravity, which is non-perturbative, and it is realized based on a new symmetry principle, the quantum scale invariance. We'll talk more about quantum scale invariance and the link with asymptotic safety in a moment. So here's a brief recap of asymptotic safety via the functional renormalization group. So the central object here is this scale-dependent effective average action, formally a linear combination of all possible diffeomorphism invariant operators. And now starting from the classical Baire action in the UV that interpolates between the Baire action and the standard quantum effective action in the IR, the flow of this equation is dictated by the Betti equation over here. And asymptotic safety basically predicts a value for a non-Gaussian fixed point, that is a fixed point of the renormalization group scale, when k, the renormalization scale, goes to infinity, with at least one of its coordinates being different from 0, and with a finite number of relevant directions. I will define what a relevant direction is in a moment. So the first requirement ensures UV completeness, while the second requirement achieves predictivity. Now, asymptotic safety basically asks whether scale symmetry is a fundamental principle of nature, even in the presence of quantum fluctuations. And by scale symmetry, I mean symmetry with respect to the renormalization scale. So typically, quantum fluctuations break scale symmetry, making the theory and its cappings scale-dependent quantities. However, you can recover scale symmetry at a fixed point, at a renormalization fixed point, where the effective dynamics no longer depend on the renormalization scale k. And this can be done in two ways. So one way is asymptotic freedom, which is a kind of trivial realization of the scale symmetry in the sense that it switches off all the interactions and effects of quantum fluctuations. So you are in some sense back in a classical incarnation of scale symmetry. And the other way is asymptotic safety, which is a truly quantum version of scale symmetry. And it relies on the interactions and quantum fluctuations being present in order to achieve this scale symmetry regime. And again, by scale symmetry, I mean that the couplings do not depend on the renormalization scale k. And this is possible due to the existence of a fixed point here, and given the importance of the existence of these fixed points, let me briefly sketch how this mechanism works. So if you start with a dimension-full coupling, V-bar, you can write down the dimensionless version of this coupling in cutoff units. And now if you take the scale derivative of this full expression, you can see on the right-hand side that the blue term indicates the classical contribution given by the canonical mass dimension of the couplings. And the red term is the quantum contribution, and it's precisely the balance between these two terms, the mechanism that generates zeros of the beta function. Here's a very naive example: is if you have this beta function with #1 and #2 being two numbers, and then if they carry opposite signs, you have the chance of achieving a non-trivial fixed point at 0 of the beta function. And of course, one of the main goals of the program is to actually compute those numbers and see if we can find solution of the fixed point equation. Not an easy task, by the way. So let me take a break and give you a pictorial representation of what is going on. So it is useful to think in the theory space as the space parameterized by the couplings associated with the operators allowed by your symmetries. Now, a single point here represents a theory parameterized by gamma k. And when you start integrating out the fluctuations, this point will move in this space, making trajectories. And one way to compute those trajectories is by using the Vetter equation. I'm not going into the details here because that is another talk, but let me say that when you send the renormalization group scale k to infinity, if you are lucky, you reach a fixed point, and while sitting at the fixed point is quite boring, the vicinity of the fixed point is very interesting. So suppose you compute or you take the derivatives of the beta function with respect to the couplings and evaluate it at the fixed point coordinates. This defines the stability matrix, and I will call the critical exponents as minus the eigenvalues of this stability matrix. And these C's here measure the distance between one point in this space and the fixed point. So when C increases, you are running away from the fixed point, and when C decreases, you are approaching to the fixed point. And now, if the critical exponents, the minus the eigenvalues of this stability matrix, are negative, I will call them irrelevant directions. And you can see that in order to hit the fixed point, these integrations constants have to be set to 0. So, and when the critical exponents are positive, that is our relevant direction, this quantity decreases insofar as k increases. So these integration constants now are just free parameters. And now these relevant directions define the so-called UV critical surface around the fixed point. And this defines the critical exponents define this UV critical surface. And I will say that the theory is predictive if the dimensionality of this UV critical surface is finite, because you have to set a finite number of integration constant with the experiment. And of course, there's a lot of evidence supporting the existence of a fixed point in the pure gravity sector with a finite number of relevant directions, not only in the Einstein-Hilbert setting, but also by including higher order operators. Okay, so now coming to gravity matter systems. If pure gravity is asymptotically safe, that is nice, of course, but we still have to couple it to matter and see if the entire system formed by quantum and gravitational fluctuations is asymptotically safe or UV complete. So we would like to basically answer the question of what happens with the non-Gaussian fixed point that we have found in pure gravity when you include matter degrees of freedom. And of course, the tricky thing here is that you have the determinant of G and the inverse of the metric everywhere. So by doing the linear split of the metric, just the kinetic term, which involves the determinant of G and the inverse of the metric, will generate an infinite tower of vertices involving graviton lines and matter field fluctuations. With these vertices, you can close the Feynman diagrams and generate matter self interactions and also non-minimal interactions between matter fields and curvature. One example is this diagram here, where this line represents a scalar field, always contains some derivatives in front of it. And this kind of diagrams shares or features the same global symmetries of the kinetic term, namely the Z2 symmetry and the shift symmetry, where when you shift a scalar field by constant. Now, it turns out that those interactions generated by the kinetic term cannot feature a Gaussian fixed point, a fixed point with all its coordinates being equal to 0. And there is a symmetry argument behind that. So if you start with a scalar kinetic term, plus a quartic self-interaction with a capping C, capital C, you see that the structure of the beta function associated with the dimensionless version of this capping C takes the following form, where this A naught, that A naught depends on the gravitational couplings generated by the kinetic term. Now, if you plug C equal to 0, which corresponds to the Gaussian fixed point in the matter sector, and assume that there is a non-Gaussian fixed point in the pure gravity sector, A naught does not vanish. And therefore, the beta function associated with C will be different from 0. This tells us that this non-Gaussian fixed point in the asymptotically safe quantum gravity matter system does not admit a Gaussian fixed point in the matter sector. And now let me go to a more general case with P is a matter capping. And if you have a Gaussian fixed point, you might have a non-Gaussian fixed point depending on the theory you are looking at. And when you turn on the quantum fluctuations, there is a shift, as we already saw in the previous example, of the Gaussian fixed point. But when the quantum fluctuations are too strong, these curves do not cross the horizontal line anymore. So you won't get a real value of the fixed point. And the only way to discriminate if you are here or here is by doing things. That means to choose a truncation of your theory space and to put the gamma k inside the Bettich equation and to compute the beta functions. And that was exactly what we did. We chose a quite sophisticated truncation of the theory space in Euclidean spacetime. So our gravitational action is given by the Einstein-Hilbert action, complemented by a cosmological constant, with a gauge fixing and both sector on top of it. And we consider only one single scalar field, the shift symmetric scalar field. So if we start with a kinetic term for this scalar field, plus this non-minimal interaction between the Ricci tensor and the scalar field, we find a fixed point, a suitable fixed point for asymptotic safety. But if now you consider the quartic self-interaction, we didn't find any fixed point suitable for asymptotic safety. And well, that was more or less my mood when I was working on this project. And now, if you consider this another non-minimal interaction between the Ricci scalar and the kinetic term, we found a suitable fixed point. But when you consider now the quartic self-interaction and the non-minimal interaction with the Ricci tensor, no fixed point was found. However, when you include everything and you put everything on the table, you find a fixed point suitable for asymptotic safety with a finite number of relevant directions. And more importantly, the fixed point that we have found when you turn off the matter sector is absolutely compatible with the fixed point that we have found in pure gravity. Okay, so let me go to the conclusions. The inclusion of these two non-minimal couplings is crucial in order to get a suitable fixed point, and mimicking what Agustin did in his talk. Here's the QR code where you can find the paper. The results obtained cover previous works and are compatible with the latest result, like the essential RGS scheme, where Benjamin Knorr include all the terms up to 4 derivatives. There are a couple of phenomenological applications that we have developed in this scenario, specifically to feed Stravinsky-like inflation. The paper will appear, I hope, finger crossed, in a few weeks. And now, if you turn off gravity as a spin-off, we found that there is an evidence for a new shift symmetric universality class. So the spectrum of critical exponents that we have found in that paper are quite new. So you can also, that was a paper that appeared last year, or sorry, this year, and you also can find the paper in archive in the second QR code. Okay, so thank you very much for your attention.
All right, we have time for questions. There's one question here.
Hi. Excuse me. In Horndenski theories, for example, I'm curious. There are some relations between the coefficients of some of the terms that you write down that come from the condition of there being only 3 propagating degrees of freedom. I was just curious, how does your work relate to that?
I remember that we were able to express, because in Horndenski theory you have a couple of G's, right? That depends on the scalar field and the kinetic term. So if we find a suitable set of these, you can go from a general Horndenski theory and express that Horndenski theory in terms of this Lagrangian. And
so this falls into the class of Horndenski?
Exactly, yeah. That falls into the class of the Horndenski theory, but the only thing, if I remember correctly, because we did the calculation a couple of months ago, was that one of the Horndenski functions was free, in the sense that it has one parameter that you can choose that parameter in order to go. So it's not one-to-one, the map of the Horndenski set and this Lagrangian. But yeah, and in the application to inflation that we use, we also compare to Horndenski-like inflation. Yep.
Okay, there is one more question over there.
Yeah, so you mentioned that the fixed point is actually boring, and but my
Sitting
question.
at the fixed point.
Sorry?
Sitting at the fixed point.
Yeah,
fixed
but
point.
if it is so boring, can you actually solve it analytically?
No.
So why is it? It's not boring then.
Yeah, maybe it's not boring, but I think that the most interesting part of the fixed point, at least under my opinion, is actually the vicinity, because when you linearize,
I understand your point.
Yeah.
But do you have any idea how I would solve the theory there analytically?
We have had some discussions with my advisor, with Frank, but not at this point.
Okay.
Yeah.